With the advent of multi-wavelength surveys from Hubble telescope, now the global stellar mass functions can be determined to up to a very high redshift now. However, those high-Z observations are only limited to relatively high massive galaxies with their stellar mass larger than few times 10 to 9 solar mass. And for local galaxies, large surveys can cover dwarf galaxies as small as with stellar mass as small as 10 to 8 solar mass. In particular, those surveys reveal that this abundance of dwarf galaxies depends. I mean, the relative abundance of the dwarf galaxies depends strongly on the environment. In the massive clusters, there seems to be a very marked upturn, shown by the red data points in the luminosity function of cluster galaxy. In the luminosity function of cluster galaxies. However, this marked upturn is absent in the stellar mass function of the field galaxies. So such difference probably suggests that an evolution in the star formation behavior in those low mass galaxies, in the low mass halos. That's because, according to the lambda CDM model, those cluster dwarf galaxies must be accreted at an early epoch. So they must carry information about the star formation activity at that time. So hopefully, if we with those data, with those observations combined, we can get a relatively complete picture of the cosmic star formation history. In order to infer the cosmic star formation history from the observations, I adopt a purely empirical model. For the central galaxies, this model simply relates the star formation the star formation rate with the mass of the host halo and the redshift through some parametric functions. The function we adopt is simply a piecewise power law with 3 power indices, alpha, beta, and gamma, and 2 characteristic halo masses. So the alpha controls the star formation rate in massive halos, and the gamma controls the star formation rate in low mass halos. And for satellite galaxies, we adopt a very simple tau model with a characteristic Quinton timescale. So we can make all those parameters to be redshift dependent, so that we can build up more sophisticated models. In principle, we can build a very complex model in the first place, so that we can fit whatever constraint, we can fit whatever observational constraint we have. However, by doing so, one may risk overfitting, and it's very likely to get fake information from the data. So instead, what we do is to start with the simplest model, in which all the model parameters are independent of redshift, and we build up the model bit by bit. And we justify every extra complexity introduced into the model using Bayesian evidence. That means only the extra complexity that improve the fitting significantly are accepted. So this makes sure that for a given set of observational constraints, the model we built is not overcomplicated, but yet still give good fit to the data. I'm going to present two models. The first model, Model A, is only required. The Model A is constructed from the global stellar mass functions. A simple redshift dependence or alpha will make the model work really well. They fit the stellar mass functions quite good. However, this model underpredicted the abundance of cluster dwarfs. And the second model, Model B, is constructed from the stellar mass functions as well as the cluster galaxy luminosity functions. And it seems that the finite upturn of the cluster galaxy luminosity function requires gamma depends on redshift in a very complicated way. And this gamma controls the star formation rate in low mass halos. Okay. Now let's look at the predictions of those two models and see what those different observational constraints can tell us about the cosmic star formation history. In this slide, I show the star formation efficiency as a function of halo mass and redshift. The star formation efficiency here is defined to be the star formation rate in the central galaxy divided by the mass accretion rate of the host halo times the universal baryon fraction. To the left is the prediction of the first model. We can see that the star formation is most efficient in halos that lies in a very narrow mass range, which is between 10 to 11 solar mass and several times 10 to 12 solar mass. For model B, everything is the same. Everything is same with model A in halos bigger than 10 to 11 solar mass. However, but in halos with mass lower than that, the situation is a bit complicated. A higher redshift, for example, at redshift 4, which is the red bands, the star formation efficiency in low mass halos is as high as 1/10, and seems depends on the halo mass very weakly. And at lower redshift, the star formation is very strongly quenched, and the transition between these two phases of star formation activity happens between redshift 3 and 2. The star formation rate density. The two models predicts very similar star formation rate density at redshift lower than 2. Both of the models predict the faster decline from redshift 1 to redshift 0, and during this time interval, the star formation rate density is mainly contributed by the by Milky Way sized halos, which is the green bands shown in the figures. However, when it comes to higher redshift, the two models are in contrast with each other. For example, for Model A, the star formation rate density declines quickly with the redshift. While for Model B, the star formation rate goes almost flat, show no sign of decrease. And at that time, at high redshift, the star formation rate density is mainly contributed by halos of the order of 10 to 10 solar mass. So that means, although at early epoch, the Milky Way mass halos have not formed, but the dwarf halos, which is 10 to 10 solar mass, are quite abundant at that time. And as I have shown in the previous slides, those halos are the host of star-forming dwarfs. Okay, let's compare the model prediction with the with the observations. It seems that model A is more compatible with the observations, because the observation shows a very clear trend that the star formation rate density declines with redshift. However, before we make that conclusion, let's look further into the model predictions. For example, let's look at the star formation rate function. The star formation rate function is just the number density of galaxies in each star formation rate bin. And we can see that the model A seems too shallow to match the observations, and because the observation, so at the low star formation rate end, the slope of the observation is quite steep. Well, model B reproduces the observed star formation rate function quite well. So here the question, why is the integrated star formation rate density is lower than the prediction of model B? I think one possible reason is that the star forming dwarf galaxies predicted in model B probably is missed in the observational samples due to the detection limit. Okay, with the empirical star formation model we got from the observations, and by following the merger trace of dark matter halos, we can predict the star formation history of present-day galaxies. In this plot, I show the star formation histories of 3 types of galaxies. The red lines are the cluster centrals, or the CD galaxies, or BCGs, the brightest cluster galaxies. And the green lines is the green lines are the Milky Way mass galaxies, and the purple lines are the dwarf galaxies with the stellar mass lower than 10 to 8 solar mass. Those galaxies follow distinct star formation histories. For the most massive galaxies here, the star formation rate reaches the maximum at a very early time, roughly at redshift 3, between 3 and 4, and declines exponentially with the e-folding time only about 1 gig-year or so. While for Milky Way mass galaxies, the star formation rate peaks at about redshift 1, and after that only declines by a factor of few. Well, for the star formation history of the dwarf galaxies, let's just look at the solid line, which is the prediction of model B. We can see that for this model, the star formation history can split into 2 stages. We can see that there's an initial starburst, which occurred about 10 billion years, roughly 10 billion years ago, and last for 1 gigayear or 2. And then the galaxy enters a relatively quiescent phase. During that phase, the star formation rate is much lower, but keeps as a constant until today. And this inertial burst is not expected from model A. Actually, this two-stage star formation history of dwarf galaxies is supported by the recent survey of nearby dwarf galaxies. Those colored lines in the right figure are the average star formation history of nearby dwarf galaxies of different morphological types. We can see that no matter whether it is a dwarf spheroidal or dwarf irregular or spiral galaxy, all of them have experienced an birthday star formation period when the universe is younger than 3 gigayears old. That is the plateau in the left corner of the figure. Okay. Now let's look at the assembly history of the present galaxies. So galaxies can build up their mass either through in situ star formation or by accretion of nearby galaxies. So for the most massive galaxies, although the star formation rate reaches the maximum at redshift about 3, and then almost stops after that, we can see the cluster centrals grows almost linearly with the time after the star formation peak. That is due to the accretion of nearby satellites. Well, for the Milky Way sized galaxies, they build up their mass quite late. At redshift about 2, those galaxies, the progenitor of Milky Way sized galaxies is only as small as is only of the order of 10 to 9 solar mass. Well, for the dwarf galaxies, so those dwarf galaxies experienced an inertial burst, and then those inertial bursts contribute almost 50% of the present-day stellar mass. We can see that the assembly history of those dwarf galaxies is very similar to the history of those cluster centrals. But the later increase in the mass of those dwarf galaxies is due to in situ star formation. So we can compare it with the cluster centrals. Those dwarf galaxies must have a stellar population that shows strong bimodality. 50% are very old, and the other half is quite young. Okay, in summary, we infer the average star formation rate in dark matter halos from the observed stellar mass functions at different redshift combined with the Liouville function of local cluster galaxies. Data on dwarf galaxies seems to suggest a new characteristic redshift, about which the star formation efficiency in low mass halos must be enhanced relatively to that at lower Z. And we predicted the star formation history and the mass examiner history of present galaxies. Those galaxies of different masses show distinct star formation histories. Especially, I want to emphasize that those dwarf galaxies have two stages of star formation with a strong initial burst. The massive galaxies form stars early, but examined much later. While for Milky Way-sized galaxies, they formed quite late. They build up their mass mainly after redshift 1. Okay, that's